Okay, hello all of you, welcome back. And sorry to say that I have handled something urgent, so I cannot start the lesson punctually. Now, today we would proceed to the concepts, right, of this one. This is on chapter 34. So last time I asked you two important questions in your classwork, right? Do you still remember what are that? We asked you first question is about can you think of some enthalpy terms in which delta of combustion equals delta H of formation? Okay, that is the first question. The second question, we will talk about something about utilization. I will leave it later. So go back to the first question. Under what situation will we record delta H of formation being equal to the delta H of combustion? So in order to tackle the problem, I just take a glimpse of it, and some of you can either think of delta H of combustion, but you cannot think of delta H of formation at the same time. Now you are going to consider both delta H of combustion and formation all together. So how would you tackle the problem? Let's take a look on the first one. Now it depends on the condition. The condition should be for the formation, you are going to write the equation such that you can express one mole of substance is formed from its constituent element in the standard state under standard condition. Now take a look on this, right? So this is the first requirement. While the second requirement is on the firm formation, the combustion. Combustion usually refer to the reaction between the fuel and oxygen. So you may see that fuel and oxygen, and here comes we will call the term burned in oxygen completely under standard condition. So usually, if you think of this term, you may have the following. Now, first of all, for the formation of NO2, okay, for the formation of NO2, can you say this equation being equal to the delta H of combustion of N2 gas? Now take a look on this. Can we say so? Now we are going to consider with consideration of two statements. Okay, first of all, if I write down this, I can say it is a delta H of formation of NO2. Okay, but if you want to talk about the delta H of combustion of nitrogen, so complete combustion, they will turn it to NO2 like this. So because you are going to talk about 1 mole of N2, here comes 2 moles of NO2, okay, and 2 moles of O2. Is that clear? And such that we can call that delta H of combustion of N2. In other words, while you talk about the definition, you may always see the word 1 mole per mole, right? And which means that this concept, this one should be in per mole. Can you get my point? For nitrogen, I thought there should be 1 mole of nitrogen should be burned. So if I say it like this way, can you say that these two equations, you talk about the same thing? Now, if you want to talk about that equation, the equation, they are the same, right? But the difference lies on the multiple of 2. Now, can you get my point? So the magnitude of these two heat change, okay, it is just a double of one of the other. Can you get my point? So if you know that is a concept, these two, they are not the same. Is that clear? So you will do it at the same time with the consideration of the two enthalpy terms, such that you are talking about the same equation with the same stoichiometric coefficient. Can you think of one example in which it meets? Now, just recall your memory about the classwork that you have done. Can you suggest one examples in which it meets that requirement? The delta formation of substance is equal to the delta H of combustion of another substance. Leichen, what do you think?
Combustion of carbon.
Combustion of carbon. Carbon in terms of what? What is the stable form of the carbon as the standard state?
Graphite.
In terms of graphite. So if you want to talk about as a complete combustion, so you may write down C plus O2 to form CO2. So for this equation, I can tell it as delta H of formation of CO2 gas, because you talk about 1 mole of carbon dioxide is formed from its constituent element in the standard state. Okay, at the same time, I can also express it as delta H of combustion of C graphite. Now, so you have to take a look on that very clearly. Okay, it is delta H of combustion of C graphite. Remember, but not telling you it is carbon. Remember, you need to tell the most stable state of carbon being graphite. Well, that data, you also talk about the same thing, but this time our main body to tell is the combustion 1 mole of graphite. So this is the main body is 1 mole of graphite. Can you get my point? So once you talk about the same equation with the same stoichiometric coefficient, is not multiple of one the other, that too is the same. Can you get the point? Okay. I do hope all of you can get it. And I can see one more example given suggested from Chen Huiting. It is also correct, right? The burning, the combustion of sulfur to form SO2, and also the delta H formation of sulfur dioxide. You talk about the same thing. Yes, correct. Can you think of do you mean that whenever you think of this and you can directly jump to the conclusion that you are talking about the same thing? Now it depends on this. How about this? Now, if I change a little bit, how about carbon monoxide? Can you do the same thing by telling we have got delta H of formation of carbon monoxide being equal to the delta H of combustion of graphite? Can I say so?
Yes.
Yes. Somebody say yes. Okay. Deng Junhei, what do you think? Can I say the delta H?
Yes. Yes.
Yes. Of this. Now, how many of you would say yes? Could you please put a tick? If not, a cross. Oh, quite many of you who say yes. How about the others? How about now I see some of you who still haven't told your choice. Wang Xinghin, what do you think? Ma Jialok, Li Qing, Hong Jiahian, and Zhang Xiwei, Wang Yilong, what do you think? Now, the best way is to pick up those students who say no. Okay, Chen Huiting, what do you think? You say it's not right. It's not correct. Why isn't it? Why is it wrong? Now, first of all, if I say this one, delta H of combustion of graphite being equal to delta H formation of CO, do you mean that is the delta H formation of carbon dioxide is equal to delta H formation of carbon monoxide? A burning of graphite produces different products depending on the situation. So take a look on our definition. What is meant by delta H of combustion of graphite? Now, for this, no problem, right? While you say so, no problem. How about this? I just want to tell this part.
Okay, incomplete combustion.
Yes, the carbon monoxide can only be formed when the carbon carbon undergo incomplete combustion. So can you get my point? So for the delta H of combustion, the enthalpy terms will show you that you are going to have complete combustion. Can you see that? So be aware of the saying, right? While you talk about delta H of combustion of something, it is you are going to think of the completely burnt products. So you take a look at carbon as example. The carbon undergo complete combustion to form the only product carbon dioxide, but not carbon monoxide. Can you get my point? So we cannot say that carbon delta H of combustion of C graphite will turn to CO. Can you get my point? So which means this one is not correct. For writing this equation, I can only express it as this, but cannot express as carbon delta H of combustion of graphite. Is that clear? You got it? So what's more is on your work. I can see someone, for example, they did not give me the answer with showing the stick symbols. So once again, the stick symbols really matters. For example, if we talk about, remember the delta H, we talk about enthalpy change. We talk about the difference in the enthalpy level of the two chemicals. Okay, with the two chemicals, which is one should be higher, which is lower, the heat content, what I mean is, so it really depends on the physical state they're having. So water, H2O gas, and steam, H2O, gaseous state or liquid state, they are having different enthalpy level. So what is the hidden message? If you in the equation doesn't tell you anything about this, we do not have any idea of what you're going to talk about. Remember, while you in this topic, you should, you must, oh sorry, I changed the word. You must state the physical state of all chemicals. Okay, please mark it. You have to state all those. Now, and that is question one. Any questions so far? So, which means that delta H formation of certain substances is being equal to delta of combustion. That is very situational, right? Not all equations can have this type of relationship. Okay, you get my point. Now, how about this? Delta H of neutralization. I asked you guys the 4 different types of delta H, right? So you may find that 4. So which one would have the largest magnitude? Which one would have the smallest magnitude? The largest one is Honda, do you know which one would have the largest value?
Strong acetone, strong alkali.
Yes, the combination of strong acid and strong alkali. So which means that it is the first one. The first one would have the largest value. So which is the more negative delta H of neutralization. This is for that one. While which one he will have the least negative value? Which one? Now this is number 1, the most exothermic. And these two, how about these two? They are more or less similar, right? Yes, this is the ammonia and the phenolic acid, this one. Now this is the combination of weak acid and weak alkali. Okay, so this one, it is the least negative delta H of neutralization. So the main reason lies on the enthalpy needed or the energy needed for the ionization. Okay, so underline the term ionization. So it's not just weak acid that they will undergo ionization, but also weak alkali, ammonia, will also need to be ionized. So while that type of bond breaking process would require energy. Can you get a point? You got it? So it is the response to your two classwork questions last time. Any questions so far? Now, if not, remember what you need to talk about is on the 1 mole of water to be formed. How about this? Can you say this type of a delta H of reaction being equal to the delta H of neutralization for this case? So being equal to number 1, the first statement, no. I can see some will say no. But hey, so what is the relation? 2 mole, yeah, 2 mole of water. So can you relate that two terms? What is the delta H of this reaction? This will be 2 times. Yes, 2 times of the delta H of neutralization. So remember, this one you talk about per mole of water form. But on the equation, you may find 2. So which means that if you write down the delta H of neutralization, the equation to be considered is just the half of this. So with with setting the number of moles of water being 1 mole. Can you get our point? So only having this will show you it is delta H of neutralization. While on top of this, the equation is the multiple of the 2. So if you want to talk about the molar quantities, right, you need doubled, okay, of the acid and alkali. So of course, double amount of water will be formed. So which means that for the release of heat based on this equation, so it is double. You get it? Okay, questions? Now, today we are going to show you one activity on the determining the enthalpy changes on combustion of alcohol. And if time allows, I will also show you some experimental method, right? And to determine the delta H of reactions later on. Because I can see that time is not so sufficient. We would have introduction of this part first of all. Determining the delta H of change of combustion. So this is the experimental method, okay? So we talk about those different types of delta H of reaction. For the following pages, we talk about how we can measure these enthalpy terms experimentally, okay? So remember, this is one of the experimental method to tell how to measure the delta H of combustion. Now, take a look on that. First of all, I will show you the lab video shortly. What you read it is I would like to ask you the two items. First of all, your science principle. What is a principle, underlying principle? So what is the mathematical treatment of the data? Once I've collected the data, how will you tackle how we arrive at the answer? And 3, any errors of the experiment. Is this something similar to physics? Right, we always talk about the measurement, the calculations, and here comes the error analysis. Do you know the meaning of the word errors? So we have got so many different types of errors. Have you all been taught about that in physics? Errors. 學過未啊？ something like human error, right? Subjective, something like subjective, right? And also we talk about the measurement error, right? We talk about the collection of data, random error. Do you still remember that? The flipping of coin, right? That is a very authentic example, right? We flip a coin with a flower, with a sign of flower facing up. Okay, first time it will be this. So can you say the conclusion is that the flipping of coins, the flower must always facing up, or you cannot, right? So it's something, the understanding of random error, something about statistics. Now I'll show you the video shortly. Now this is the one. Please take a look on the chemical principle, the science principle they're having.
The aim of the experiment is to establish the enthalpy of combustion of ethanol. The enthalpy of combustion of ethanol is the energy released when 1 mole of the substance is completely burned in oxygen. 1 mole of ethanol is completely combusted in oxygen. It's very important that the equation has to be balanced. We begin by weighing this ethanol with the lid on, then place under the copper can.
A copper can is used as it conducts heat. 50 centimetres cubed of water, which is equal to a mass of 0.05 kilograms, is added to the can.
We wait until the temperature settles, then record the start temperature.
We then light the spirit burner.
A heat shield is used to stop some heat being lost into the environment.
We continue to start through the experiment without the thermometer touching the bottom of the can to ensure an even heat distribution. When the desired temperature is reached, you blow out the burner and wait till the thermometer has reached its maximum temperature.
We finish by putting the lid back on the spirit burner to avoid ethanol evaporating into the air, and weigh the spirit burner again.
The 5 measurements that were made during the experiment: the mass of ethanol burner before, the mass of ethanol burner after, the mass of water, temperature of water at the start, temperature of water at the end.
We worked out the change of the mass of the ethanol to be 0.76 grams and the change in temperature of the water to be 20 degrees Celsius.
The enthalpy of combustion of ethanol calculation. Suppose 0.76 grams of ethanol has been burned and the temperature of the water has risen by 20 degrees Celsius. The heat energy gained by the water is calculated using the formula EH equals Cm delta T, where C is equal to the specific heat capacity of the water and has a value 4.18. M equals the mass of water being heated, and in this experiment it is 0.05 kilograms. Delta T is equal to the rise in temperature in Celsius. So EH is equal to 4.18 times 0.05 times 20. This is equal to 4.18 kilojoules.
We can now calculate the heat energy released on burning 1 mole of ethanol. The gram formula mass of ethanol is 46 grams. 1 gram gives us 5.5 kilojoules, so 1 mole gives us negative 253 kilojoules. The reaction is exothermic, thus it is negative.
Errors which may account for the difference between the data book value and these values are that heat has been lost into the environment and also incomplete combustion has occurred.
All right.
You need to change all that as well.
No, they based on your numbers.
Finish this part. So can you follow? So what is the science principle of this experiment? What are the mathematical treatments that you are having? And tell me something about the area. First of all, what is the science principle behind? How will you know the delta H of combustion, Shanoka?
The conservation of energy.
Conservation of energy. Please elaborate more.
Because the amount of ethanol burnt will cause a release heat, and then to heat up the water. And then water will be heated up, and then some of them will vaporize. Yes, and then we can calculate the amount of water loss to find out how many water has been turned to vapor, and then we can in turn calculate the amount of heat released per gram of methanol burnt.
Okay, so the principle lies on the heating, how much, what is the mass of the water evaporated, is it?
Yes.
Yeah. Agree? Can I have
temperature change of water?
Sorry?
Temperature change of water.
Oh, what you just see is the change, temperature change of water. Okay. And Jia Hongming, what do you know about the science principle behind of these experiments?
Other than
is a video that we show is different from that in the book? What it means the principle, are they the same?
They seem to be the same.
Seem to be the same. So can you tell me your understanding of the principle?
Other than the energy conversion, I think there's another science principle, which is heat conduction. As methanol is burnt, its chemical energy is converted into thermal energy, which is heat, and then the heat will be transferred, will be conducted into the copper can, which in turn will transfer heat to water, therefore raising the temperature of the water, and then we can calculate the amount of heat that the methanol produced.
Now, so the underlying principle is on the term, yes, that both are correct. Yeah, you talk about change temperature rise of water, but not evaporation of water. Now, because if you want to talk about evaporation of water, is quite difficult to measure. Now, if you because I don't know anything about whether or not the phase change is due to what. Okay, so in physics we usually deal with the boiling of water, right? You talk about vaporization, but not evaporation, because in order to reduce the complexity of the calculations. But in this experiments, the water, it is assumed not to be vaporized. Okay, no boiling. So the water would have a different, we've got the rise in water temperature due to the heat transfer from high temperature here, around here, to somewhere low temperature here. So heat will be transferred from the site where the burning is formed to somewhere cooler. So you can define the area. Now, so this is what you will define, that is our system. Because you are now in the surroundings, so the remaining part is our surroundings. So what you're going to do is to indirectly measure the amount of heat released from the ethanol vapor here, okay, by assuming all 100%, right, of heat is totally transferred to the water, okay, such that you can, from the rise of the temperature, okay, from the rise of temperature, I know what is the heat released from burning of the alcohol, okay? Can you get a point? Now, before I talk about errors, right? Please just get to know the principle first of all. Okay, the principle. Of course, you may argue, Mr. Chin, do you would all heat will be totally transferred to water? Of course not, right? There may be something lost, right? Some heat will be lost. So this is our error analysis. Okay. So this is our principle. So so second point, could you please write here? The principle is that the heat absorbed by water. So you know there is a temperature rise, right? Which is equal to the heat released or from the burning of alcohol. Okay, while you would say the burning is a complete burning. Do you understand? So that is our principle. And shall we introduce to you the container? We will not use beaker. We will use a copper can. We call that calorimeter. Not calorimeter, is calorimeter. Do you see the word? Calorimeter. Calorimeter is the container which is also involved in your calculations. Now it's made of copper. It's a good heat conductor. Do you understand? So if let's take a look on the procedure, right? So you are going to have a certain amount because we are going to measure the heat absorbed by water. So the calculation should go to mc delta T, right? The mass of water, the specific heat capacity of water, as well as the temperature rise of water. So the mass of water should be carefully measured. Now, usually we use volume, and you can directly jump to the mass of water. Why? The density of water is equal to 1 gram per cm cube. Okay, so you use this relationship to directly jump to this. And then with the spirit burner, now this is a spirit burner, so it can be placed with different types of alcohol. Now you may see the methanol, 1 carbon alcohol, right, in this example. And from the video, you see is ethanol, 2 carbon. So you're going to here burn it, weight the difference here. You see that? The weight the spirit burner, and afterwards we weigh the spirit burner. Do you see that? Okay, so from this, I would know the mass of the alcohol burnt by measuring the difference in mass of alcohol. So I can do something like this. Okay, now you see that we weight burner weight, right? And then you place the spirit burner under the copper can. You're going to light the burner and burn the methanol, stir in the water, and after about 3 minutes, put off the fire and immediately measure the maximum temperature of the water. Now there's a procedure, right? The experimental finding, because I measured difference, I know the mass of the alcohol burned. And because of that, I will know the delta I know the delta T of water. Delta T of water. Can you see that? So because I know it is 150 grams of water with the specific capacity. Is this no need to memorize this term? The exam paper will be given to you. And then the rise in the temperature is just the highest minus lowest. Here comes 45.1 degrees Celsius. Okay, the thermometer show you as degrees Celsius. You need to change it to Kelvin, such that you can cross them out the unit of temperature in the calculations. And then also you're going to cross out this part, the gram, and leaving behind is on the joule. I express it in kilojoule. So this is the amount of heat absorbed by water. So we call it amount of heat transferred to water. And heat released is due to alcohol, right? So you know the difference in the mass of the alcohol, okay, over is molar mass. So you would know the number of moles of the alcohol burns. It's not necessary to burn 1 mole of fuel, right? But in your calculations, you can use this to project what will happen if I burned 1 mole of the alcohol, right? It's simply doing that calculations, the heat absorbed by water over the number of moles of ethanol burned. So here comes this part. Now remember, once I write down heat produced, so here it carries no unit, okay? Because heat produced is already has already told you the direction of the amount of heat. It is from the system to the surroundings, okay? So you are going to write down the enthalpy terms being a vector this time. So you are going to express it as minus here, which tells you it is exothermic. So you are talking about 2 terms, okay? First, if you are going to talk about amount of heat produced when 1 mole of methanol is burned completely. So if I write down this one as a topic sentence, the answer should be given no sign because heat produced already directly referring to the direction of heat flow. Okay, you get my point. But if you write down the enthalpy change of combustion of methanol, you have to give it a sign. Only by giving a sign will you know that the direction of a heat transfer. It is a heat released reaction. Can you get the point? So, in short, the calculations should go with the assumption that all heat transfer to absorb from heat released from the burning of the methanol will be totally transferred to the water such that you can measure. So this is our calculations. We assume 100% transfer, okay, from here to here, right? And the calculations you are going to do backward and trace back, and finally you come up with the delta H of combustion per mole of the fuel burnt. Do you understand the chemical principle? All those something about calculations. So here comes the principle, the calculations, and finally here comes the error analysis. What have been mentioned in the errors? What have been mentioned about errors in the video? Or to your understanding, what do you think? Is it accurate?
And not accurate.
Yeah.
因為佢 burn 緊嘅時候，佢啲 heat 唔係，即係有機會佢係 lose to the surrounding， 唔係 transfer 咗去嗰個copper can 度，咁所以咧就唔係100%。
So can you tell something? What is mean by surroundings? Where is surroundings?
佢由佢即係佢嗰個 點講咧？即係佢嗰個burner 佢隔離嗰啲 air 咯。
Yeah, air will absorb heat, right? Air also absorb heat. What else would also absorb heat? But you did not calculate in it, but you're not taking into consideration while you do the calculations. The air absorb heat. What else?
Copper can.
Yes, the copper can also absorb heat, right? Even though it's a metal, it has a relatively low specific capacity, it still absorb heat. Okay, the copper container. Okay, the calorimeter also absorb heat. What else? Now, so these two, they are the main or thermal, we call it as the surroundings, right? The heat loss to the surroundings other than water. So you may find that copper can. You may also air. Okay. So these two will also be taken into account to the heat absorbed, the heat absorption. So they will also absorb heat. So in physics, people will also take into account of the heat capacity of a copper can into the calculations. Okay, in physics, you can also measure how much heat has been absorbed. You have to take in this into account by including the calculations. But of course, in chemistry, we seldom ask you to do such calculations because not all students study physics. But about the air, right, is quite hard to measure, right? Or how will you improve the design? Now we have got so many improvement of design. Okay, this is one of them. So what have been made in order to reduce the heat loss to the surroundings? What have been made? What have been added? Can you see that? 林成航。林成航 what have been added? This setup, what have been added? Now this is a so-called improved design, right? What have been added? And what is the purpose of it?
嗰個叫 draw skin 啊。
Okay,
screen 嗰個。
draw skin.
Yes.
What else?
同埋 mineral rule 咯。
Yeah. So please tell it in detail. What is the function of that two?
Draw skin 應該係即係去 prevent 呢個loss of heat due to the surrounding 咯。
Similar
即係叫做
but what is meant by surroundings? Where could you be a bit more
即係
specific?
呢個to prevent the heat loss due to the oxygen surrounding the flame.
Oxygen.
The air.
Air. Okay. So it is to reduce airflow. Okay. In short, it is to reduce the airflow because air will absorb heat. So the concept is reduce the airflow, or less air will be absorbed that type of heat. So heat will be lost. So this is the principle. How about mineral wool?
The mineral rule should be to prevent the heat loss from the absorption of heat from the copper can.
Okay, the copper can. Now in the copper can, if I have this design, would the copper can not will no longer absorb heat. Now I place it in the exterior, right? The outer surface. So, but you heat it like this way. To heat the direction of heat, it is from the water from the flame to the calorimeter directly, like this. Okay, so the question comes: so what is the purpose of mineral here? If you want to say that the mineral to block the absorption of the of copper, the mineral should be placed here, right? Why not? Why would they place it on the sideway of the calorimeter this time? What does it help? Can you get my point? So what is the use? What is the function? Acts as an insulator. Yeah. So yes, it is an insulator. First of all, mineral is an insulator. Both are correct. Okay, both two of you mentioned is correct. But the position of placing the heat, the insulation layer, well, would really affect the whole calculations later on. Okay, so if I place it next to this, which means that you just imagine, right? In cold days, you use you use the polystyrene cup to contain hot coffee, for example, right? So what is the principle? So you know that it traps the heat, right? So in other words, the heat transfer from the copper can to the air will be hindered, right, by the mineral wool. So can you get a point? Can you get a point? So the mineral wool acts as a heat insulator to prevent or to slow down or to reduce the heat transfer by conduction, right, from the calorimeter to the surrounding air. Can you get a point? So first of all, the heat insulator would not absorb too much heat, and also it would help reduce the heat transfer from calorimeter to air. So we will have the mineral wool just placed directly next to the calorimeter. Now, but any question? Do you think that this design is perfect? It's nice. It's not perfect, right? Actually, because air, conceptually, we need to have oxygen supply, right? We need to have oxygen supply. So air will still absorb heat, but less air will absorb heat this time. So we cannot have a 100% heat transfer. What's more about the drawbacks of having this design? We've got another thing, right? Because I reduce the airflow, which means that not the supply of oxygen in air will be hindered. Okay, will be hindered. So what does it cause to is the incomplete combustion of ethanol, of the alcohol will occur. Can you get a point? So this is another drawback. Once you think of too much insulation, to prevent the heat transfer to the air. Now finally you have got a draft screen, right? It stops the airflow, right? But because you stop the airflow, the burning, right, is not efficient, it's not complete. So during the process, it's not just carbon dioxide water to be formed, but also some other products, such like carbon monoxide, carbon soot, etc. So all those, I do not know the relative amount. Now, even though you'll be given that H value, I don't know the relative amount, so that we cannot calculate the answer well. But of course, what I know is that what we can predict is that if you have got a higher chance of incomplete combustion of ethanol, the heat release will become less than expected. All of you, please mark it down. Heat released will be less than expected because the fuel is not completely burnt. Do you understand? Now, no need to mention some other type of design. So that's why you need to modify the design. Now, so there are so many different ways of designing this. Okay, you can search on the web and choose one of them in which for the delta H of combustion, you can measure the value very, very close to the theoretical data. You can search it on the web. Now, what's more, here comes some other errors. For example, the evaporation of the alcohol from the wick 燈芯. This is a place while you have got a wick here, while the ethanol, the alcohol vapor, will first of all suck up through the wick, okay, and to let them vaporize so easily, and I put the fire here, right? So to facilitate the burning process. So the once I put off the fire, and the evaporation of the ethanol through the wick will still continue, okay, will still continue. So it will more or less affect the experiment, okay. No need to mention, while you burn that alcohol, right, some alcohol will just directly evaporate without burning. Do you realize while you do the alcohol burner, just like Dun Junhei, you have tried that the information day, right? You do the flame test. You may have encountered the use of alcohol lamp, or what we call it spirit lamp, or you directly soak with some cotton wool with alcohol, right? So you may just stand there and absorb quite a large amount of alcohol vapor. It's quite volatile, okay? The chemical is being volatile. So even though I measured the difference in mass of the ethanol, that doesn't mean the mass loss contribute to the complete burning of all alcohol. Can you get my point? So some evaporation of alcohol will occur. Okay, and of course, somebody may argue the experimental conditions being not standard. Okay, and also this will affect our measurements. So they will cause the value. Well, you say the value is magnitude. This is less than expected. In other words, the measurement of this will be measured as less negative, right? This is another directional term to tell. Okay, if you write down magnitude bigger than smaller than expected is smaller. If you want to talk about the delta H value, how does it affect the H value? We'll use the term less negative to tell the direction. Less negative, which means less heat is released than expected. Is that clear? Do you understand? So, how would you improve the design, right? In your classwork, show me how would you search for the delta H of combustion, a better design. In reality, we have got some better design. Okay, please search for me. Any improvement of this, okay? How would you make the design better with your explanation of some different parts added to it? Do you understand? So this is our task one, the classwork later on. Now, today, I would like to show you the calculations part, okay? Let's have a try together. Before we end up lecture, this is the final part, before we end up the lecture today. Question 1, under standard conditions, complete combustion of 0.05 mole of propane 10 gives 101 kilojoule of heat. What is the standard enthalpy change of combustion of a propane 10? So, delta H of combustion of propane 10, which means that we burn 1 mole of propane 1 mole. How much heat is released? So it is just what? It's just a multiple. It's just a multiple of this data, right? How many times larger? And you can get the answer. So can you come up with the answer for that? So my point is to take a look at the step as well, okay? I need to check the step as well. So first of all, if you write down the standard, now enthalpy change of combustion of propane 10. Now, or you use the term delta H of combustion of propane 1-mole. Now, this is the way to express. Now, please use the one-word form or short form. It is also okay. Either form, you need to put a sign negative, okay? Now, because on the equation, they just tell you heat is released. So in your calculations, you have to show the minus sign here, and then put the heat amount of heat released, okay, over what? Over the number of moles of propane 1-mole. Do you understand? So you do the same thing. 101 kilojoule over what? 0.0500 mole. So it's just a multiple, right, of that data. So what is the answer? That is question 1. What is the answer? After your calculations, what is the answer? Thẩm Quang Nhung, what is the answer? Thẩm Quang Nhung, are you here? Yeah, tell me your answer. Minus what? Yes, minus 2020 kilojoule per mole. Now, I would like to draw attention to the unit. The word joule, there should be in a capital letter J. Okay, basically most of you who want to look for bigger J, right? So remember, capital letter J, but not small letter J. Okay. So this is the way to express the answer. Of course, somebody will, if you write down something like this, now minus 101 kilojoule over 0.0500 mole, without showing the negative sign, what you can tell is just heat released by burning 1 mole of propane 1-mole. Can you get a point? So which means that you are going to do this release, the term released, to in replace to the sign. But after all, while you write down 2020 kilojoule per mole, you have to write down the standard enthalpy change of combustion of propane 1-mole being minus the data. Can you get my point? So if you write down this, this method, you need to show me this term again, standard enthalpy change of combustion of propane 1-mole. Remember to show the sign being minus value. Can you get a point? Remember, I would like to check that very carefully with you. Do you understand? Question 2. The standard enthalpy change of combustion of an unsaturated hydrocarbon X is minus 2059 kilojoule per mole. In an experiment, 0.470 of X will completely burning oxygen. That heat produced that will raise the temperature of 150.0 gram of water by 36.7 degrees. So first of all, A part, calculate the amount of heat we transfer to water. So this is what? MCWT. Remember, the MCWT should be go with the water. So please mark the term related to water. in order not to be confused. Water, the mass water. Specific heat capacity water here. While delta T, it is here. Okay, remember. Do not get confused, right? Whatever you talk about water here, you are going to circle the component about the water, the measurement about water. Now, leaving the other data untouched, okay? Do not use other data. So what you will get is 150.0 gram for for specific heat capacity water, 4.18 gram per joule per gram per Kelvin, and the temperature rise being 36.7. Now the unit, it is from degrees Celsius. I change it to Kelvin intentionally. Can you see that? I change it from degrees Celsius to Kelvin. Now by doing so, I can cross out those temperature unit, the mass unit. Okay, so leaving behind is on the gram, the joule, sorry, the joule for that. What is this data? What is this data? Are you here? Hello, 馮家軒。好，你見我？
我喺度喎，你機
23,000
the unit?
Joules per kjoules per kjoules.
Kilojoule. 23,000 kilojoule, is it?
23 kjoules.
Oh, 23 only, 23.0 kilojoule, okay? So it is 23,000 joules. Okay. B, calculate the relative molecular mass of X. Wow, quite nasty. You are going to do it in reverse, right? You are going to do it in reverse. Now, because they just tell you certain moles of unsaturated hydrocarbon per mole, it releases that type of heat. But this time, it involves that type of heat only. So what is that? So you may get to know or do some calculations, just like number of moles of unsaturated hydrocarbon. First of all, can you calculate how many moles of unsaturated hydrocarbon? The number of moles of X burned. It is something related to what? It is 2059 kilojoule. Okay, what's next? Over what? Which one should be over what? Do it in reverse. It's just one mole. So, but you have got this one, 23.0 kilojoule. How many moles do you need? So check the unit. If you find it confusing, you better check the unit. It should be 23.0 kilojoule over 2059 kilojoule per mole. How many mole will you get? How many moles?
0.0112.
112 mole. So which means that you just burned a very little amount of the unsaturated hydrocarbon, but not 1 mole. but it's enough, right? Because that we've got this, we've got this. Can you calculate the molar mass of this? You can, right? The molar mass of X, molar mass, this should be gram per mole, right? 0.470 gram over 0.0112 mole. Okay, you hold the data, right, in your calculator. So 0.470 divided by the answer. So here comes 42.1. Now gram per mole. But remember, because you are talking about LMM, so finally you are going to leave the answer LMM of X being equal to 42.1. Remember, no units. Otherwise, the final answer mark will be deducted. Now, do not write down gram per mole to express the RMM of X. Now, RMM carries no units. How about the last one, C part? Deduce the molecular formula of X. What is that hydrocarbon? You may see the term.
Unsaturated.
Yep, unsaturated. So can you, what is the homologous series you are talking about?
Alkene.
Alkene. Is it alkene? Unsaturated alkene. It can be alkene or it can be alkyne, right? Now it will be quite difficult to tell for the time being, but you can start from alkene first of all. So suppose and try to see if you can get a multiple of a integer of a whole number. Otherwise, if not, you may think of alkyne. Okay, suppose X is an alkene, so you are going to let CnH2n. Now this is the general formula. Now remember, it's the general formula. Be the formula of X. This is the molecular formula, right? So you may get it at the RMM being equal to 42.1. So what you're going to do is to calculate 12.0 n plus what? 2.0 n. Now, sorry, so this should be 2n, but not 2.2 n. It can be 2.0 because 100 being 1.0, right? Being 42.1. So you can calculate n. What is that? It's about 3. It's about 3, right? So the molecular formula of the X is what? C3H6. If I say it is an unsaturated hydrocarbon, can you tell the name? What can it be? What can it be?
Propene.
Propene, only choice, right? No other isomers. No other isomers, right? Propene. Propene. Is that clear? So this is what I would like to share with you today on the calculations. Do you find the whole thing very complicated? A bit, right? But the first of all, what you talk about is the chemistry, is to measure the delta H of combustion of a certain substance. Of course, you need the supply of oxygen, right? So we cannot have a place where there is no oxygen supply. So you still need the airflow. But you are going to. But the more the airflow, the more assurance of complete combustion of ethanol, but the more heat will also be lost to the air, right? So it will greatly affect the answer. So we are going to have a compromise. Okay, you're going to do the in between. On one hand, you're going to make the combustion more complete, but at the same time, what are you going to do? is to release the heat loss. So, for example, calorimeter to reduce certain type of airflow in order to make the data be so-called more accurate, right? With less other complexity. So this is the calculations, and the assumption should be what? All heat released from the burning of the ethanol will be totally absorbed by the water. But of course, it's not the case, right? You may find some other items nearby also absorb heat. And what's next is about the calculations. You are going to have two sets of data, one related to the mass of the alcohol burn. The other one is the something related to water. For example, you talk about the mass of water, the specific capacity of water, the delta T of water. So you need to take a look on that. So calculate the number of moles of ethanol or the other alcohol will be counted by checking the mass, okay, and its molar mass. So you are going to divide that data over this in order to get that calculations mark of this. Remember to put a negative sign. And the unit for the delta term is what? Remember, kilojoule per mole, while the J should be in capital letter. Is that clear? So this is what I would like to share with you on today, right? On delta H of combustion on the day of the experimental setup, the calculations, the error analysis. Any questions so far? So please search for me. So the classwork is your further work is to check the following. First of all, any further improvement on the calorimeter of this burning set experiment. Tell me. Second, I will show you and tell me what is the difference in the part, what is the function of the parts, which will help you get the answer. First, second is to give you one calculations, and I like to check you guys how will you get approach to the calculations clearly. Okay, only two questions. Okay, I would like to check that too. How about the others? Some of you mark it as 7766. How about the others? To your understanding. Do you find it easy, difficult, or what? So. No, it's not that difficult. It's not that easy. But to me, I would request you guys to practice more. Right? Remember this part. Once it becomes a long question, I'm sure most of you can score it perfectly. It's something about calculations, huh? Now, before we leave, one more point is about a summer supplementary lesson, right? Have your teachers told you anything about summer supplementary lesson for the time being, or have you received anything about the teacher notice on the summer vacation arrangement, the special very, very complicated, the special vacation arrangement? Have you all received this? Now let me check. Do you have it? Do you have the notice? Not yet. Let me check.
有啊，好似有嘅已經。
有啊，最新消息啊嘛。Please check for the latest news, updated 3rd of March. So you would have a you have got one more week to go, okay? Okay, we have got one more week to go before we release. So afterwards, I would have the summer supplementary lesson with you guys. Can you manage? Better than staying at home and playing computer games, right? You get bored. Yes, summer vacation will start. Of course, summer will always go with supplementary lesson. 阿俊都 Do you know it? Someone should always go with supplementary lesson. Long for it, isn't it? Okay. So stay tuned, and I will tell you the schedule. Because I need to talk to the other teachers as well, and so as to get to know the final arrangement with no clash with you. Any more questions so far? Now, if not, sorry to say that you'll be released just late for your afternoon tea, right, session. So it's time to have break. Bye-bye.